So this guy, Jason, is doing a bench press, and he slowly pushes a bar up a distance of 0.3 meters while pushing upwards on the bar with a constant force of 200 newtons. So, and the bar, for some reason, moves at a constant, little slow velocity as it goes up. So how much work does Jason do on the bar during this time? 60 joules. This is one I liked. Yeah, again, I'm thinking that in this case, F is up, and the displacement is up. So theta equals 0, so you just use that the W is equal to plus FD. So it's equal to 200 times in SI units times the distance, 0.3. So you're keeping the force in newtons, you're keeping the displacement in meters, therefore you get the energy in joules. You get 60 joules. This is on the way down. How much work does Jason do on the bar if he lowers it at a constant velocity, if that's possible? Well, so that is what I was looking for. Is it possible to be, why is it going down if I'm pushing upwards on it? Does anybody know?
The weight of the bar is greater than your force.
Yeah, exactly. There's a bunch of weight. So I guess if I just let go, it would just fall on me, and it would hurt me. So what I have to do is to lower it slowly, I have to actually push up while it's going down. That's the weight. But I guess if it's going constant velocity, I think the weight still has to equal this 200 newtons that I'm pushing up. But I must get it accelerating by just decreasing that force a little bit at the beginning and then getting it slowly moving down. And then let's do one more question on this while we're on this whole thing. Slowly lowers the bar down a distance, 0.3, while pushing upwards on the bar with a force of 200 newtons. It then pushes it up slowly the same distance back to its starting position during the complete downward and upward motion. How much total work does Jason do on the bar? Yeah, so what's happened is that it might actually, you might be expending a lot of energy, but you haven't transferred any energy into that bar. The bar ended up at rest again, and started at rest, ended up and started at the same position, which was up. So you haven't transferred energy into the bar, so you haven't done any work on the bar. 3 balls are thrown from a cliff with the same speed, but at different angles. Which ball has the greatest speed just before it hits the ground? Yeah, that's the idea, is that you're just using a conservation of energy idea here. They all start with the same energy and the same, same kinetic energy and the same potential energy. So we'll use here E initial equals E final. That's the conservation of energy. And so this 1/2 m times v0 squared plus mgh, I guess, initial, is equal to 1/2 mv final squared plus mgh final. And since these are the same, and this is the same, these are all 3 the same, then therefore I think VF is the same for all 3. That's all you need to know. You don't need to know details about the path, because gravitational potential energy is due to a conservative force of gravity, and so it just depends on the change in initial to final position, doesn't depend on the path. Hockey puck sliding along smooth ice at 4 meters per second comes to a 1 meter high hill. Will it make it to the top of the hill? And no. Okay, that's what I got as well, I think. And this is sort of now showing how energy concepts are super, super useful. You can't do this question with kinematics, I should say, because you don't know the angle of the hill. But you can do it with energy conservation. So what I'm going to do is I'm going to say let's assume it does make it. I mean, there's a few different ways of doing this. You could just find the height it goes to, but let's if it makes it to the top, so it gets up here, and this is like h final or something, and h initial is 0. So you've got, again, this. Most important equation in Chapter 7. All right. Which, I don't know why. I really have a hard time in office hours getting students to write this one down. They want to skip a bunch of steps and add in all the zeros. Plus mgh initial equals 1/2 mv final squared plus mgh final. I mean, eventually, once you get really used to it, you could maybe skip a few of these steps, but which are the zeros? Well, this one is 0, and I think that's the only one. Okay, so we've got v, and I think what I can do is divide both sides by m. So I got v0 squared over 2 equals v final squared over 2 plus g times h final. And I can solve this out. I think I want to solve for v final, right? So v final squared over 2 equals, I think it'll be 4 squared over 2 minus 9.8 times 1. This is equal to 8 minus 9.8. This is v final squared over 2. So I got negative v final squared over 2 is equal to negative 1.8. And so this is not possible to solve this. You can't square something and get a negative. So that is one way of, I guess the other, like I say, the other way is you could try to find the height. You'll find the maximum height's less than a meter, but can't take square root of a negative number. It would be an imaginary final speed, I think. A car starts with speed v initial, but the driver puts on the brakes and the car slows down to a stop. As the car is slowing down, its kinetic energy is transformed into what? Okay, so this is a new concept called this internal thermal energy, E internal. And this could be heat, this could be, I think, these scratches or that kind of noise that we were talking about at the beginning of class, but something is now lost in the system. And this one has multiple answers. You remember last time I talked about yesterday, I pushed a box that was initially at rest across the floor and then stopped pushing, and it was finally at rest. So the system is the box and the carpet. To find the box to have 0 height when it's on the floor, the initial situation is just before I push the box, and the final situation is just after I stopped pushing the box. So what I'm going to do is have it's basically this equation, but I've split it up into 3 terms on the left, which is that I'm doing some work. So this work is a positive term probably. It's going to be some term that I've added to the initial situation. And then finally, I've got a situation where I've got some kinetic energy, some potential energy, and maybe some change in internal thermal energy, like we did with that car. So I'm just asking you to pick which ones are not 0. Maybe you just have to choose one of the. Anyway, the correct answers were that the work and the delta E initial, okay, they're sort of the E internal are both going to be. But if you throw a ball directly upward, it passes some specific height on the way up, but then it passes that same height again on the way down. So if you were to neglect air resistance, how does the kinetic energy of this ball compare at that same height on the way up versus on the way down? Do you think it should be about the same or quite different? Yeah, there was no trick that I was going for here. This is the idea. So if there was air resistance, there'd be a resistive force on the way up that would be slowing it down, a resistive force acting up on the way down. Anyway, always against its velocity, so you'd have a little less kinetic energy on the way down than on the way up. But Rita raises a 10-kilogram package at a constant speed to a height of 25 meters in 2 seconds. So I think the constant speed just means that it's not accelerating, so there's no change in kinetic energy, but it is gaining energy in the form of gravitational potential energy. If she were to raise the same package to the same height in 1 second rather than 2 seconds, how would the work and the power change? Work would stay the same, power would double. Again, power is equal to the work done divided by this time, how much time. And the work done here is going to be the change in potential energy gravitational. So it's going to be mg times 2.5. And this will be the same for both. So if the delta T goes down, the power should go up. So, again, this is neglecting air resistance. A sports car accelerates from 0 to 30 miles an hour in 1.5 seconds. How long would it take to accelerate from 0 to 60 miles an hour? So I'm using mph, which is a unit of speed. But I think what matters here is that you've doubled the final speed. So I'm going to leave it in the non-SI units of mph. Assuming the power of the engine is independent of velocity and neglecting air resistance, what would be the change in time to double the final speed? It says, serve a toss-up between 3 seconds or 6 seconds. Now, so let me go over this one. You'd think you double the speed, double the time. But my idea here is that the power is independent of the velocity. So what we do here is assume power is constant, and the work done on the car by the engine, I guess, equals the change in energy of the car. So the way we look at this in terms of conservation of energy is that there is chemical energy stored in the gasoline, in the gas tank of the car, and that's being converted into kinetic energy, I guess, or, well, if it's speeding up in this case. So the power is equal to the work divided by delta T is constant. So delta T, if you rearrange this, is the work divided by the power. And so the work here is going to be 1/2 mv final squared, and you're going to divide it by the power. So if the Vf is doubled, then Vf squared increases by a factor of 4. So delta T2 is going to be like 4 times delta T1. Okay, so and 4 times 1.5 is 6. Which gas listed below contributes most to the greenhouse effect that sets the temperature of the Earth? Because this is an important effect that's been going on since well before humans were around, called greenhouse effect. Again, it's not in your textbook, this fact, but so it turns out that it is water vapor.
My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.